بسم الله الرحمن الرحيم. محاضرتنا الثانية في مادة المودرن كنترول راح تكون عن chapter 5 which is about the response and stability of state space models. وبالتالي راح نبلش في البارت الأول منها اللي هي response of state space models. بالتالي الشابتر هذا في جزء كبير منه يحاكي المعلومات نفسها اللي مرت معنا في الاوتوماتيك كنترول كورس من حيث اللي هي التايبس اوف ريسبونسز من ناحية والكاتيجوريز اوف stability اللي هي ممكن اللي تواجهنا في linear time invariant control systems. بالتالي بخصوص موضوع responses of state space models احنا في عنا 3 types of responses for LTI control systems. زي ما حكيت هذول عبارة عن they are very similar and exactly the same to the responses that were covered in automatic control course, but the difference lies in that the stability and automatic control it was covered in terms of the transfer function, while here we will cover this stability issues from the aspect of state space model, the matrices A, B, C, D. So the 3 types of responses that are covered for any LTI system, they consist of zero state response, and this is the response due to inputs only and when all initial conditions are set to 0. The other type of response is the zero input response, and it's clear from its name that zero input response that when all inputs are 0 and it will be only due to initial conditions. And the third category of response is the overall response or the total response, which is the summation of the zero state and the zero input response when the system is excited by both the initial conditions and the inputs. If we consider the state differential equation for linear time invariant control system, which we previously covered, x dot is equal to x plus bu, and as given in equation 5.1, and after applying the Laplace transfer on this equation and performing very simple manipulations, we will get equation 5.2, which give us the value of xs as a function of A matrix B and U of s and the initial conditions. So this equation 5.2, x of s is equal to si minus A inverse multiplied by x of 0, which is the initial conditions vector, plus si minus A inverse multiplied by b u of s. And it's obvious that this equation consists of 2 parts. This is the first part and this is the second part, and both parts they have si minus A inverse appearing in both of them. So if we apply or take the Laplace inverse of this equation, we will obtain the equation 5.3, which is the time response of all states, which is equal to the Laplace inverse of equation 5.2, which is the Laplace inverse of the above mentioned equation, and we split this Laplace inverse for the first part and the second part. So if we pay attention to this equation 5.3, we notice that one part contains x of 0 and the other part contains the u of s. And here we will classify or split the overall response into 2 parts. This is the part that is related to the zero input response, and this is the part that is related to the zero state response. So regarding the zero input response, it will be the first part of equation 5.3, okay, which is given in equation 5.4, and regarding the zero state response, it will be the second part of equation 5.3, and it will be in this format. So as I have said, this part and this part, they contain the SI minus A inverse, and the difference lies in that in this equation we multiply by x naught, and in this equation we multiply by B u of s. So the overall response, or the total response, as we have covered here, it's the summation of the zero input and zero state response, which is this equation, which is already equation 5.3. So if we focus our attention to the first, to this equation, equation 5.3, and regarding this zero input response, okay, and if we go back to the differential equations, we remember that if we have a system, a single differential equation, x, let me write it here, x dot is equal to ax. We remember that the solution to this system will be x of t is equal to e to the power a t multiplied by x initial conditions, x of 0. So similarly, if we extend this from the scalar single dimensional vector to the multidimensional vector, we will get this equation. Okay, we will get this equation, which is x zero input response is equal to e to the power a of t for x of 0, and here e to the power a of t is a matrix. It's not a scalar value because a is a matrix, and we will get a matrix. So this is regarding the zero input response. And if we compare this equation with this equation, then we will reach to a final conclusion that e to the power a t is equal to the Laplace inverse of Si minus A inverse, and we call this a matrix, which is e to the power at phi t, and phi t is the state transition matrix. We call it state transition matrix, and this is in time domain. In S domain, phi of S, the state transition matrix. In S domain, it will be phi of S, which is equal to Si minus A inverse without any Laplace inverse. So here there is a group of properties for this state transition matrix. We are interested on only the first one, and the remaining we are not interested in discussing them at this stage. The most important thing about phi of t, which is the state transition matrix, is that the fact that this matrix phi of t is a square matrix, and its dimension or size is n by n matrix. So we are interested in the next slides in obtaining this state transition matrix, and we will cover two methods or three methods where two of them can be applied, not the three of them. And the first method for computing the phi of t is computing phi of t using the Laplace transform method. And as we discussed in equation 5.10, phi of s is equal to si minus a inverse. And if we will go back to what we have covered in chapter 1, we know that the inverse is equal to the adjoint matrix divided by this determinant si minus a inverse. And if we take the Laplace inverse of this phi of s, we will get phi of t, which is equal to the Laplace inverse of adjoint matrix of si minus a divided by the determinant of si minus a. So this is a direct and straightforward method where we can find phi of t, the state transition matrix, based on Laplace transform method. The second method for computing of phi of t is based on similarity transformation to DCF or GCF. As we previously discussed, that any given state space model can be transformed to one of the two parallel canonical form, whether we can convert it into DCF or JCF, but not both, depending on the eigenvalues. If the eigenvalues are distinct, then we convert it into DCF. While if the some of the eigenvalues are repeated, then we convert it into the JCF. So here we can compute phi of t by similarity transformation to DCF, and this assumes that the eigenvalues of the matrix A are distinct eigenvalues. So regarding the steps from 1 till let's go to the remaining slide, from step 1 to step 4. This is exactly the same as we have covered in the previous chapter regarding the similarity transformation to DCF. Finally, we end up with those AT, BT, CT, DT, and here we are interested in only AT, the transformed matrix AT. We are interested in it, and this matrix, in case of DCF, it will be a diagonal matrix as shown here. And after getting this AT, we will find the state transition matrix using this equation, which is T multiplied by e to the power dt multiplied by T inverse, and this is T inverse, and this is e to the power dt. And don't forget that the diagonal matrix, it contains the diagonal eigenvalues, the eigenvalues in its diagonal. So e to the power e to the power dt will be all diagonal matrix with the eigenvalues raised to the exponential of the eigenvalues multiplied by the time, and in this way we will obtain the state transition matrix. So this is the second approach, where the eigenvalues are distinct. But if the eigenvalues are not distinct, then we should proceed into the transformation based on JCF, not DCF. And as I have discussed previously regarding the DCF, all the steps from step 1 till step 4 will be identical to what we have covered in the previous chapter in order to obtain the transformed matrix AT of this JCF form. And AT, we will obtain it using this formula, and it will be a Jordan matrix as we have previously covered. And based on that, we find the state transition matrix phi of t, which is equal to the e to the power AT, which is equal to T e to the power j multiplied by T multiplied by T inverse. So these are the main methods that are used for the calculation of the state transition matrix. And let's go to the examples. The first example I want to mention and to clearly identify the following fact, that when we speak about the state transition matrix, we are speaking generally about the zero input response, and all the response will be due to initial conditions. So there is no need to define the input, and there is no need to define the B vector or matrix. So we are interested in this case only in defining the A matrix, and this is what happens in this example. A is only defined while we don't need the input or nor the B matrix in order to proceed in the solution, since we are speaking about the zero input response, and the input is, in this case, will be 0. So the first part of the state differential equation will be covered only, and the remaining part will be cancelled due to the fact that u of t is equal to 0 by applying the superposition theorem. So it's required to find the state transition matrix based on the two methods, the Laplace transform method and the similarity transformation method. So as we previously covered, the calculation of the state transition matrix phi of t based on Laplace transform method, we are interested in finding the Si minus A inverse, and finally we get this matrix. And if this is, which is the same as phi of s, but here the difference between this matrix and this matrix is that in this matrix we have distributed the denominator in the among the four terms, while here the denominator in this equation, the denominator is collected. So this is phi of s, which is equal to Si minus A. And if we want to find the phi of t, not phi of s, because it's the state transition matrix, then phi of t will be the Laplace inverse of Si minus A inverse, which is the Laplace inverse of the four terms of this matrix, 2 by 2 matrix. And finally, after applying the partial fraction reduction and performing all the required procedures to get the Laplace inverse, then we get this 2 by 2 matrix for the state transition matrix. The second method is based on the similarity transformation, and in order to know which of the methods will be used, the DCF or the JCF, then we should find the eigenvalues, and the eigenvalues, it's obvious they are distinct. So based on that, we will use the DCF. So for lambda 1 we calculate M1, for lambda 2 we calculate M2, and finally we get the transformation matrix. And also finally we will get e to the power dt, e to the power lambda 1, lambda 2, and the remaining items are 0. So this is e to the power dt, and phi of t is equal to t multiplied by e to the power dt multiplied by t inverse, as was previously given. And finally we will get this answer, and it's obvious that this answer and this answer, they are 100% the same. So regardless of the method by which the state transition matrix is calculated, the final answer should be the same. Now, after covering the responses of LTI systems in state space models, we will cover the stability of control systems in state space. And here we for the stability of control systems, we consider the state space model given in ABCD, and we assume that it's given a closed loop transfer function. And when dealing with transfer functions, we know the definition of transfer functions, that all of the initial conditions are set to 0. So this equation is already known to us, and we have previously derived it in chapter 2. M of s, which is equal to the closed loop transfer function, is C multiplied by Si minus A inverse multiplied by B plus D. So regarding this inverse SI minus A inverse, as I have discussed previously in this lecture, SI minus A inverse is equal to the adjoint matrix divided by the determinant of SI minus A, and if we substitute this into this equation, then we will get this equation, and if we will simplify it further, we will get rational polynomials n of s and d of s. N of s is equal to this, and d of s is equal to this formulation. And we want here to pay attention that the numerator polynomial represent the zeros of the closed loop transfer function, while the denominator polynomial represent the poles of the closed loop transfer function, which is also called as the characteristic equation of the transfer function. So the roots of the characteristic equation, which is the roots of the SI minus A determinant, they determine, as we have covered in automatic control course, they determine the stability of the system. So the stability from automatic control or transfer function perspective, it's controlled by the determinant or the roots of the characteristic equation, or the determinant or the roots of the SI minus A. Okay, if we compare this with the eigenvalues of matrix A as previously covered in chapter 1, then the eigenvalues of any matrix A, they are calculated through this equation, lambda I minus A. So here we have two equations, Si minus A and lambda I minus A. They have very close similarity, and if we compare the eigenvalues equation, lambda I minus A is equal to 0, with the characteristic equation Si minus A is equal to 0, we reach to a very nice conclusion that the roots of the characteristic equation in the S-plane are exactly the same as the eigenvalues of matrix A. And this is clearly covered in this point and this point, that for stability conditions, the eigenvalues of matrix A is exactly the same as the roots of the characteristic equation Si minus A is equal to 0. This means that every pole of M of S is an eigenvalue of matrix A. So if we speak in terms of the transfer functions, we speak about the roots of the characteristic equation, or the poles of the closed loop transfer function, and which is the same and exactly the same as the eigenvalues of matrix A in state space representation. And since we are dealing with transfer function equation 5.16, we know, as we have covered in the decomposition of transfer function chapter, that transfer function, characteristic equation, eigenvalues, and stability, they are independent of the similarity transformation, because transfer function is always unique, while the state space representation is not unique, and it's multiple in all cases. So based on the above discussion, we will discuss the stability conditions in state space model, which is exactly the same as the stability conditions of automatic control course, but the automatic control course, it was the perspective was from the roots of the characteristic equation. Here it will be not the roots of the characteristic equation. We will speak about the eigenvalues of matrix A. So Beebo stability, bounded input, bounded output, it's related to the zero state response, and when all initial conditions are set to 0. And for what's meant by a Beebo stable system, a Beebo stable system is a system, if we excite it with a bounded input, its output should be also bounded. Okay, and there is a condition that we covered exactly previously in the automatic control course, that for BIBO stability, all eigenvalues or the roots of the characteristic equation, they all should be in the left hand side of the S-plane, or they should be simple on the j omega axis. This means that no root should be located on the right hand side of the S-plane, or should be multiple eigenvalues on the j omega axis. Okay, so this is the first type of stability, which is the BIBO stability. The other type of stability is the zero input stability, and this is related to the initial conditions when we excite the system with initial conditions and all inputs are zeros. And what's meant by this condition or this stability? Zero input stable system if we excite the system with finite initial conditions and its response approaches zero as t approaches infinity, then the system is zero input stable or stable. So the necessary condition for zero input stability is that all eigenvalues of the matrix A, they should be in the left half side of S-plane. And for zero input stability, the system will be unstable if one of the following condition is encountered. The first condition, if any simple eigenvalues, they lie on the j omega axis and none of the eigenvalues on the right hand side of S-plane. Okay, and if the other condition, if at least one root on the right hand side or multiple roots on the j omega axis. So if we compare the BIBO stability with the zero input stability, we will find that the only difference lies with the simple roots that lies on the j omega axis. The simple roots that lie on the j omega axis in BIBO stability, it's considered as stable, while in zero input stability, it's considered as unstable. And based on that, we will come up with the overall stability that try to organize and make an umbrella for the two types of stability. And this total or overall stability, we excite the system with inputs and initial conditions. So the necessary and sufficient condition for the overall stability is that the eigenvalues of the matrix A or the roots of the characteristic equation, they should be in the left hand side of S-plane. And this is obvious in this stability condition in this table. Okay, so all the roots or the eigenvalues, they should be in the left, then the system from overall stability aspect is stable. And the system will be unstable if at least one root on the right hand side or multiple roots on the j omega axis. Okay, one eigenvalue, what I mean. And regarding the difference between BIBO stability and the zero input stability, we have generated this new stability condition, which covers when we have simple eigenvalues on the j omega axis without any roots or eigenvalues on the right hand side or multiple roots on the j omega axis. So here at least simple eigenvalue, no multiple order roots on the j omega axis, and none of the roots in the right hand side, then the system will be marginally stable. And as I have discussed previously, these conditions, the overall stability conditions, they are exactly the same, same conditions as we have covered in the only thing and the only difference is that in automatic control course we were speaking about the roots of the characteristic equation, while here we are speaking about the eigenvalues of matrix A. So they are the same, they are not contradicting stability conditions. And let us start with the examples. Here we have four systems, and we want to check the stability of these systems by determination of its eigenvalues. And for the first system, it's obvious that the eigenvalues are all in the left, so the system is stable because all of them they have negative real part. Regarding the second system, the two eigenvalues they are on the right hand side, and the system is unstable. Regarding the third system, we have one eigenvalue on the j omega axis, and the system is marginally stable. And regarding the last one, we have simple eigenvalues on the j omega axis, and correspondingly the system is marginally stable. After covering all of the related things to the stability and input response, to the stability and response issues, then we will cover a few examples in the next examples. Here we have a system, a control system that is 2 by 2, and it's required to find phi of t based on Laplace transform and similarity transform method. Okay, and as we have previously covered, when we are speaking about the state transition, this means that we are interested in the first part of the state differential equation. U of t is not, we are not concerned about U of t because U of t is equal to 0 in this case. So based on Laplace transform method, we find Si minus A inverse, and finally we find phi of S, and after that we apply the Laplace inverse and find this phi of t after applying the partial fraction reduction and all related issues in the process of the Laplace inverse, and we get finally phi of t as shown in this matrix. And using the similarity transformation, we find the eigenvalues and they are distinct. So the matrix, we can use the Vandermonde matrix in this case, and the T matrix is given in this form, and e to the power dt, it will be this matrix. And if we proceed in this example, phi of t will be finally phi of t will be this matrix, and which is exactly the same as the procedure that was used for the Laplace transform. The second example is example 5.4. Here we have a system of 2 by 2, and it's from the problem statement, it's given that we have an initial conditions and nothing is related to the input. So this means that we are speaking about the phi of t and u of t is 0, and it's required to find the output response. And in this example, we find phi of S, which is equal to Si minus A inverse, and then after that we step to phi of t, which is equal to the e to the power at, which is equal to the Laplace inverse of this matrix, and finally we will get this phi of t. And in the final requirement of this example, we should find x of t, which is equal to phi of t multiplied by x of 0, and x of 0 was given in the problem statement, it's this vector 1 1, and finally we get x1 of t, which is equal to this, x2 of t, which is equal to this, and it was required in this example that we need to find y of t. Y of t in the problem statement it was given as y of t is equal to this case, to this equation. Y of t is equal 1 minus 1 multiplied by x of t, and xt is a vector, not a scalar. So if we go back to our location and we continue the example solution, then y of t is equal 1 minus 1 x of t, and if we perform this multiplication, finally we will get this formula for y of t, and the response of this system is covered in this figure. Here x1 of t, and here x2 of t, and here is y of t, and all of them, they are of sinusoidal nature. Next we will switch to the next example, and this example is something different from the previous examples. This example, if we notice that here the initial condition is given, and here we have u of t in it, and u of t is defined as unit step input. So this system is excited by both the initial conditions and the input. The size of this system is 2 by 2, and we will find the overall response. We will find the overall response, which is due to the initial conditions from one side and due to input from the other side. So this is what we mean. X of t will be this by this equation. It will be this equation, and if we proceed, we find Si minus A inverse, which is equal to phi of S, and phi of t, which is the Laplace inverse of this equation, and after performing the required calculations, we get this equation, and the zero input response will be 5t multiplied by the initial condition vector, and we will get this formula regarding the zero input response. This is the first part of the solution. We are interested in finding the overall response. So regarding the overall response, we should switch in the second part to the zero state response, which is the Laplace inverse of phi multiplied by b multiplied by u of s, and u of s in our case is a unit step, so u of s will be 1 over s, and the zero state response will be Laplace inverse of s, phi of s multiplied by b multiplied by u of s, and we will get finally this. If we perform the calculations, we will finally get zero input, zero state response as this, and finally the overall response will be the summation of the zero state response plus the zero input response, which will be given in this, and this is x1 and this is x2. And if we go back to the problem statement, we see that here we have two outputs for this system. It's obvious that we have two outputs for this system. If we pay attention to y of t, here it contains two rows. Okay, so this means that we have y1 and we have y2, and if we perform the calculations, we will obtain this formula, and this is y1 and this is y2, and y1 is given in this equation, y2 is given in this equation, and this is the overall response of the system. This is y1, which is equal to x2, and this is y2, and here also x1 of t is given. So regarding the examples that does not contain any additional information, I will not discuss, but you are asked to solve all of the examples in this handout. Okay, so we will switch to the next example. Okay, it's an example that contains information about the u of t, and here nothing is mentioned about the initial conditions. This means that the output will be due to zero state response only, and no initial conditions are there. And this system, it's obvious that it contains two inputs and it contains two outputs. So this is a MIMO system. This is a MIMO system, two inputs, two outputs. And here it's required to find the response using the following inputs. The first input is unit step, and the second is a delayed unit step function. And if we proceed in the solution process, we will find Si minus A inverse as given in this equation or matrix, and phi of S will be the same, and phi of T will be a Laplace inverse of this, and we will apply Laplace inverse of this matrix. Okay, and if we are interested in the zero state response, which is equal to the Laplace inverse phi of S multiplied by B multiplied by U of S, and B phi of S B U of S will be, this is phi of S, this is the B, this is the U of S. If we perform this multiplication, finally we will get this equation, and if we apply the Laplace inverse of this equation, we will get this, and Y of T, which is equal, as I have said, its two outputs will be this is Y1 and this is Y2 of T, and this figure shows Y1 and Y2. The examples that does not have any additional informations I will not cover, but you should read and solve them completely. So in this manner we have completed this chapter, and hopefully I wish that you understand everything covered in this lecture.